Hello, everyone. I am sorry that I'm not here today. I actually am here. Some of you guys will probably see me over the course of the day, but not able to be in the classroom today. And for that, I apologize. So, what I want to do, because I do think that there was a little trick to some of the stuff that we did yesterday, what I want to do is I want to work you through those just to make sure that we're all on the same page with those before we move on to what we're doing today. Miss Bowles probably has already given you guys the note sheet for what is today, what is new for today. Because after we're finished going through this, I'm going to just jump right back in to this note sheet that was given about rational exponents, and we're going to make it about halfway through it today. That's it. And then tomorrow we'll go over it, and then we'll finish it because the backside of it's a little trickier, and it's kind of one of those things where I feel like it would be better for me to be there. So, anyways, what I want to do now though is check this homework, make sure that we're all on the same page, that we understand what we're doing. So let's go. You hopefully checked numbers 4, 5, 6, and 7 while I've been talking. Those were ones that I just wanted you to type them into your calculator, make sure you understood how to find square root, second x squared, how to find cube root, math 4, and then of course how to find fourth root, which is 4 math 5. If you can't remember that, again, press those keys and make sure you can find those in the future, because come to the test on Thursday of next week, I'm not going to tell you. You got to find them on your own, which shouldn't be a big deal. All right, so let's get started with these problems, some of which are easier than others, but I want to go ahead and work you through all of them just to make sure there's no issues. So remember, if we have a square root symbol or a radical symbol like that and there's no value here, that means it's understood to be a what? Square root. If you said it, that's right. Good job. So anyways, we're going to break that down by trying to find the biggest perfect square that goes into 150. Because I know for sure 150 itself is not a perfect square. Remember, you can always check. Just go second x squared, type that 150 in, push equals. If the value is a decimal, it's not a perfect square. So quick check so you can always remember. So what I like to do is I like to divide it by 2. 150 divided by 2 is 75. 75 is not a perfect square, but it's my starting point. I don't want to try a perfect square above 75. So real quickly with my calculator, I just work through them. 150 divided by 64. That's the next one below 75. That doesn't work. 150 divided by 49. Doesn't work. 150 divided by 36. Doesn't work. 150 divided by 25. There it is. 25 goes into 150 6 times. So because 25 is a perfect square, like we said, that gets to escape that radical as a whole number 5. So now all of a sudden I can multiply 5 by 5 and I get 25. And then, of course, the square root of 6 stays trapped inside, and that has reduced down to 25 times the square root of 6. Okay? Very simple. I hope that you guys remember that. Number 10, the cube root of 875. Again, we've moved in because, see, there's a number there. It's not square root anymore. It's cube root. So I'm not looking at my perfect squares any longer. I'm looking at my perfect cubes. Again, you have that little chart with you. Hopefully you have it. You're going to get a better chart soon. But I know for sure that I'm looking at my perfect cubes, and 875 is just not in it. Bless me. So 875 is not a perfect cube. So just like the last one, we want to do it the same way. We want to divide it by 2. And then we want to check to see if that value is a perfect square. No, it's not. It's 437.5. So we want to work our way down. We want to work our way down, checking all the perfect cubes to determine which ones, if any, will go into 875. So again, looking at my list, the smallest one below 437.5 is 343. So I check it. I divide it. 875 divided by 343. doesn't work. So then I try 216. That's the next perfect cube. 875 divided by 216 doesn't work. So then I try 125. 875 divided by 125 absolutely works. So 125 is the biggest perfect square that goes, I'm sorry, I just said that wrong. It's the biggest perfect cube that goes into 875, and it goes in there 7 times. So that's exactly how we're going to break this one down. Okay, the cube root of 125 gets to break out as a whole number 5. And then, of course, that 7 has to stay inside. So this answer, since that 5 has nothing else to combine with, is simply 5 times the cube root of 7. All right, that's number 10. Then we have one that was a fourth root, C. So now we're not dealing with square roots. We're not dealing with cube roots. We're dealing with fourth roots. So we're looking at our perfect fourths. Again, I look at my paper that I gave you guys yesterday. We went all the way through the first 10 that got us to 10,000. 567 is definitely under that, and it's not on my list. So, like all the other ones, I divide it by 2. That's 283.5. I'm not going to try perfect fourth that's below or above 283.5. So I just start kind of checking them off. 256. Will 567 divide evenly by 256? Nope. So I try 81. Will 567 divide evenly by 81? Bingo. There it is. 81 is the biggest perfect fourth that goes into 567. So that's how I'm going to break it down. I'm going to use the fourth root of 81 times the fourth root of 81. It went into 567 7 times. So that 81 being a perfect fourth gets to break out of there, and it breaks out of there as a whole number 3. Okay? So now we've got negative 3 and positive 3 on the outside. We're going to multiply those. That's negative 9. And stuck inside the fourth root is 7. So it's negative 9 times the fourth root of 7. Okay, hopefully you got that one right. Number 14. Again, we're back to square roots, but we're adding this variable piece. So let's do that. I'm going to leave the 3 alone for the time being. We're going to try to find the biggest perfect square that goes into 252, because I know 252 is not one. You know, I've dealt with this enough, and I think probably you have too. 252 is not a perfect square. You can check it. Second x squared, 252. It's always smart to check it, but it is not. Okay, so I move on, and I divide 252 by 2. And that gives me 126. I'm not going to try a perfect square above 126. So here I go. I'm just going to start kind of checking them off. So 121, 252 divided by 121 doesn't work. I know 100 won't work. 252 divided by 81, nope. 252 divided by 64, nope, close. 252 divided by 49, nope. 252 divided by 36, and there it is. 36 goes in there 7 times. And then I always like at the end, personally, to do the variable. Save it for last. Now, you don't have to do it like that. For me, I find that it just kind of keeps it organized better, and organization is good for me. So I'm going to keep that k to the 5th, and I'm going to save those variable pieces until the very, very end. So the 36, again, being a perfect square, it gets to break out as a 6. So here's what I have as far as number goes. 3 times 6 is 18. That's outside. But then you've got that 7 that's trapped inside. So that takes care of all those numbers. Okay, everything's where it needs to be. But now I got to focus on the variables. Remember, variables, they work differently. Okay, they don't have to be perfect squares. They don't have to be perfect cubes. They don't have to be perfect fourths in order to come out. What they have to do is be multiples of the index. Remember, the index here, the root is 2. So here's how I go about this. How many times will 2 go into 5? Twice, right? That's it. So because 2 goes into 5 twice, k gets to come out twice. But think about this. That's 2 multiples of 2. right? 2 multiples of 2 got to escape. Well, 2 times 2 is 4. So only 4 of those k's were able to actually come out of this and escape from the radical. Well, if 4 came out, but there were originally 5, how many still remain? Well, definitely 1, k. Technically, that's k to the first. So there's my answer. It's 18k squared times the square root of 7k. Okay, I know a couple of people were kind of getting confused on that. I didn't have just a ton of time to answer a bunch of questions yesterday because we were kind of finishing up like right as the class was ending, except for 5th period. So therefore, I wasn't able to answer the questions I would have probably enjoyed answering. But anyways, that's number 14. Let's go to 16. It's another square root, and this one's actually a lot easier because the square root of 49, that is a perfect square. It gets to come out as a 7. So from a numerical standpoint, everything escapes. And 3 times 7 is 21. Okay? Now, since that happens so easily, now I can go ahead and focus on the variables and how they get to come out. Don't forget, this is understood to be a square root, so that's a 2. So here's my process. How many times will 2 go into 9? 4 times, right? 4 times. So x gets to come out 4 times. But that is 4 times 2. 4 times 2 is 8. 8 x's actually were able to come out. But how many are there? Well, there were 9. So if 8 came out, how many got stuck inside? 1. So x stays inside. Technically, that's x to the first, stays inside, and now that takes care of the x. Now, how about the y? How many times will 2 go into 16? Well, 2 goes into 16 8 times. So y actually gets to escape 8 times. And again, 2 times 8 is 16. 16 of those y's were able to escape. Well, there is only 16 of those y's. That means that every one of them got to escape, so you do not leave any inside. So the only thing that's left inside is x. So my answer is 21, x to the 4th, y to the 8th, times the square root of x. I hope that makes sense. Let's go and do a cube root one. See, that's a cube root. Now, I know that this looks like there's really no number here. Technically, that's a -1. And remember, since it's a negative and we have an odd root, we're going to go ahead and let that come out. The square root of -1 is -1. So I'm going to let negative go ahead and escape. Okay? Now, I'm positive there's going to be some stuff left inside. So I'm going to go ahead and leave that. And here we go. How many times will 3 go into 14? 3 goes into 14 4 times. So that means r gets to escape 4 times. Now, that's 4 multiples of 3. 4 multiples of 3 is 12. 4 times 3. If 12 escaped, but there were 14, how many are still left in there? 2. So r had to stay inside that radical twice, r squared. And then lastly, how many times will 3 go into 9? Well, 3 times. So s gets to come out 3 times. Well, 3 times 3 is 9. That's all of them. They're all out. Nothing left inside. So our answer is negative r to the 4th s cubed times the cube root of r squared. Okay? Now listen, sometimes this number right here, it gets really, really close to what you pulled out. Just make sure that it's really clear that that is the index to your radical. Okay? Just make sure it's really clear. All right, number 20, we've got 4th root. And we've got a number here, 243. So I'm looking at my list of perfect fourths. It's the same one that you have. And I see no 243 on it. None. So I know that I'm going to have to break that down. Or maybe not. Let's see. 243. If I divide that by 2, 243 divided by 2 is 121.5. I am not going to try a perfect fourth above 121.5. So 81. 243 divided by 81, that's the first one. And sure enough, it goes in there 3 times. So 81 goes in there 3 times. Now, again, I like to put my variables all the way over to the right and just basically elect to choose to simplify those after the numbers. See, the fourth root of 81 gets to escape. Okay, the fourth root of 81 is 3. So we have 3 outside, and we have the fourth root of 3 inside. Now let's see what else we got. How many times will 4 go into 5? Once. So m gets to come out once. That's 1 multiple of 4, right? 1 multiple of 4 is 4. 4 m's got to come out. Well, if there were 5 m's and 4 of them got to come out, only 1 remains. How many times will 4 go into 13? 4 goes into 13 3 times. So n gets to escape 3 times. 3 multiples of 4. 3 times 4 is 12. 12 of these n's right here get to escape. If 12 of them get to escape, how many are left? Just the 1. So my answer here is 3mn cubed times the fourth root of 3mn. I hope that if you were struggling with this yesterday at all, it's starting to clarify itself. You're welcome to try the other examples. Tomorrow, I have the answer sheet for this entire worksheet. I'd be more than happy to let you see it tomorrow to see if you did these right, if you worked on them on your own. But anyways, let's do this last one, and then we're going to move into today's note sheet. So first, I'm going to leave 5 alone, and I see that 112. Right? 112 is definitely not on my list of perfect fourths. If you didn't have your list of perfect fourths, don't forget you can check it going 4, math, 5. And then you plug that 112 in there, and you see if it gives you a nice value. It will not. But 112 divided by 2 gives me 56. So I'm going to try on my perfect fourths below 56. The only one that's really below 56 that'll help me is 16. So let's check it. Will 112 divide evenly by 16? And the answer is yes, it will. So 16 is the biggest perfect fourth that goes into 112, and it goes in there 7 times. Now don't remember, the way I told you I like to do it is I like to put my variables over here to the side, and I'm going to come back to those in a minute. Because right now I want to focus on my variables, or my numbers. You see, the fourth root of 16 is a 2. So 2 gets to escape that radical. So now here's where I've got all my numbers. Ready? 5 times 2 is 10. 10's outside. And then that 7 gets trapped inside. Make sure that 4 is clearly a root, so we don't get confused with anything that might go right here. Now we can focus right here. How many times will 4 go into 24? Divide if you want. 24 divided by 4. That's 6 times. C gets to come out 6 times. See, that's 6 multiples of 4. 6 times 4 is 24. 24 of these C's came out. Well, there are only 24. So that means no C's get left underneath. All right, next. How many times does 4 go into 13? Divide it. 4 goes into 13 3 times. D gets to come out 3 times. See? 3 multiples of 4. 3 times 4 is 12. 12 of these D's came out. So how many is left? Just the 1. So the answer is 10 C to the 6th, D to the 3rd, times the fourth root of 7D. All right? And that is how you were supposed to do last night's homework assignment. If you'd like more practice, look, there's several more that are just calling your name. And like I said, tomorrow, if you'd like to ask questions about those, I'd be more than happy to go over them with you. We should have a little bit of time. Okay, so that's it. That's it for last night. That's about 20 minutes in. So we're going to use the next 20 minutes or so to explain this concept of rational exponents. Now, when I say rational, I like to say, when I say rational, I mean fractional. Okay? That's kind of the way I like to remember. A rational exponent is a fractional exponent. Okay? A rational exponent is a fractional exponent. So if we talk about rational exponents, we know that you're dealing with some situation where a base, like a, is raised to a fractional exponent, like we have here with 1 over n. Okay? So rational means fractional. Now, here's the deal. When we have rational exponents, fractional exponents can also be written as a radical. Okay, so let me go back and remind you real quick. There were three parts of a radical. You had the actual radical sign, okay? You had the index, the root, and you had the radicand, right? Those were the three major parts that we talked about. Well, as you see here, that is exactly from the writing that we did, the notes we did yesterday, that's exactly what we have here. You see, in a fractional exponent, a rational exponent can always be written as a radical, and here's how it works. Here's how I like you to remember it. Okay, you ready? I can always take a rational exponent and write it as a radical. The denominator of my fractional exponent is my root. The radicand is the base. The base is the radicand. And if there is some value up here, it is the exponent of the radicand. Now, anything raised to the first power is itself, so you don't really need to put the 1 there. But that's how it works. So if I have a to the m over n power, it's a fractional exponent. A fractional exponent can always be written as a radical. So the denominator is the root, the base is the radicand, and the numerator is the exponent of that radicand. So nth root of a to the m power is another way of writing a to the m over n power. So that's what we're doing, okay? We are taking these and we're going in both directions. We're going to convert between exponential and radical form, and then we're going to turn right back around and we're going to go from radical to exponent. And that's going to be the end of what we do today because I'm not here and I don't want to go to the back because it is a little bit more difficult, and I would like to be there to make sure to answer any questions that you have. So let's get started on this, and then I'll give you a homework assignment, and then I'll come back tomorrow, answer any questions that you have, and then we'll move on to the back of this note sheet. Okay? That still puts us on track to take the test next Thursday, so don't sweat. The fact that I'm not here today is not going to affect us. So here we go. See how we have a fractional exponent? X to the 1/4 power. Well, again, when I see that and the question says that, hey, write this in radical form, I know that I need to go ahead and put my radical. What did I say? The base of that fractional exponent is the what? The root. This is the 4th root of. The base is the radicand. And it's raised to what power? The 1st. Now, if I wanted to put that 1, I could, but I don't need it. So, another way of writing x to the 1/4 power as a radical is the 4th root of x. And that's it. That's really all there is to this. So let's kind of work through some of these. I want you to notice how this whole thing is raised to the fractional exponent. The whole thing. So therefore, I'm going to write my radical. The denominator is the root. Now, don't forget, if that's a 2, do I really need to include it in this spot? No. If you write it there, is it going to hurt anyone? No. But I don't need it because it's the square root. Now, what is the radicand? Well, the base of 1/2 is 15n. So 15n, the entire thing goes underneath the radical. And since it's raised to the 1st power, I'll leave it be. Okay? So here, we've got 24 to the 1/3 power. So if I rewrote that, again, I've got my radical. And you can go in whatever order. The base of your exponent is your radicand. The denominator is the root. and the numerator is the exponent. Now, I want you guys to notice something. That's the cube root of 24. That's the first one that I think we have the ability to actually simplify. And this says simplify if needed. Well, this one definitely can be simplified, okay? Because I know there's a perfect cube that goes into 24. The cube root, or the perfect cube that goes into 24 is 8. And it goes in there 3 times. So the cube root of 8 becomes a 2 times the cube root of 3, which gets trapped inside. And there's my answer now, completely simplified. 2 cube root of 3. Okay? All right, next. We've got 7 to the 2/3 power. So here's what I'm going to do. I'm going to go ahead and draw my radical because it's a rational exponent, a fractional exponent. The base of my exponent is the radicand. The denominator is the root. And the numerator is the exponent that goes on my radicand. Now, 7 squared is actually 49. Now let's check that. Okay, 49 itself is not a perfect cube. If you divide that into 2, that's 24 and a half. So the only thing that could possibly go into it that's a perfect cube is 8, and it does not. So I actually cannot simplify that down, so I leave it, the cube root of 49. Okay, look at number 5. Again, I see a fractional exponent. Look, a fractional exponent. I see a rational exponent, and I know that can be written as a radical. I put the base of my exponent as my radicand. I put the denominator as the root. Since that's the square, I don't need it. And then, of course, it's raised to the 7th power. Now, go back to what we did yesterday. How many times will that understood 2 right there go into 7? 3 times. So K gets to escape 3 times. And again, 3 multiples of 2. 3 times 2 is 6. If 6 K's came out, but there were 7 originally, how many is left inside? Just the 1. So my answer is K cubed times the square root of K. I hope that makes sense. All right, look at the next one. Here we've got 3 raised to the 5/4. So if I write that as a radical, because it's a fractional exponent, my base of my exponent is the radicand. The denominator of my exponent is the root. And the numerator of my exponent is the exponent that goes on my radicand. Well, there's a couple of ways you could go about this. You could try to reduce the 3 to the 5th power. But I think there's an easier way. Think about it. Treat 3 like it were x. Treat 3 like it were x. And that said x to the 5th. Wouldn't you say, well, hey, how many times will 4 go into 5? Well, 1 time. So 3 would get to escape once. But that's 1 multiple of 4, right? Well, if that's 1 multiple of 4, and there originally were 3 or 5 3's, how many still remain? Just 1. So my answer in simplest form here would be 3 times the 4th root of 3. I hope that makes sense. That could be a tricky one if you don't look at it carefully. Number 7. Again, I see the fractional exponent. It's a rational exponent. I can write it as a radical. All of the base is in these parentheses. So I'm putting that whole thing in the radical. That's my radicand. The base of, or the denominator of my exponent is the root. And the whole radicand has to be raised to the 3rd power. So it's essential that we put that AB in parentheses. Why? Well, if I didn't, look, let me show you. If I didn't put it in parentheses, I just put the 3 there like that. What does it look like is being cubed? It looks like only the B is being cubed. But all of AB was in parentheses. So all of AB is being cubed. There's one way around that. You could leave it the 4th root of, But you could take each of these, a and cube it, and b and cube it, and you could have written it like that. Either one is 100% perfect for me. It's really just your call. Okay? Next one, we've got, we've got a fractional exponent. So I know it can be written as a radical. So then I'm going to take my negative 6x, which I know is down in my radicand. The denominator of my exponent is my root. And then this whole thing, the negative 6x, the whole thing is being squared. Okay? Now, if that whole thing is being squared, then that means we have the cube root. Negative 6 squared is 36, and x being squared is x squared. Now let's think about 36. Let's see if it can be simplified. 36 divided by 2 is 18. So I'm looking at my list of perfect cubes, and I'm checking to see if anything below 18 goes into 36. 8 is the only thing left, and it does not, so this will not simplify. You leave it just like this. Okay? All right, next one. Please don't multiply the 7 by the 12. Remember, in PEMDAS, exponents come before multiplication. So therefore, what I'm going to do, because the instructions here tell me they want me to write it as a radical. So that means that 7 is on the outside of the radical. Okay? Now remember, inside that radical, you have the base of your exponent, 12w. On the outside, the denominator of that exponent is the root. Well, that's understood to be a 2. I don't need to write it. And that 12w is simply inside being raised to the first power, which I don't have to write it. So that looks like 7 times the square root of 12w. Now, time out. I know this is where it gets a little tricky, but isn't there a perfect square that goes into 12? Yeah, 4. 4 goes into 12 3 times. Okay? So here's what this means. 4 gets to escape as a 2. So outside we have 7 times 2, which is 14. Inside that radical we have 3. And then look at that w. Will 2 go into 1? No. So that w stays underneath there with the 3. So my answer is 14 times the square root of 3w. Okay? So that is how we take them from exponential. Remember, they're fractional exponents. Every one of these. Fractional exponents. And that's how we know we can take them and rewrite them as radicals. Now, let's go the opposite direction. Now, we've got these radicals, and we want to write them as exponents. So what I like to encourage people to do is this. Immediately look at your radicand. That's the base of your what? Say it. It's the base of your fractional exponent. So I like people to go ahead and write the 16 and then write that little line that's indicating, hey, that's got to be a fraction. So what do I know about these parts of my fraction? Well, I know that the root is the what? What did we say a minute ago? The root is I kept on saying it. The root is the denominator of your exponent. The denominator is the root. So this has to be cube root, so the denominator has to be 3. Now, was that 16 raised to a power? Absolutely not. So a 1. So this is 16 to the 1/3 power. Okay, look at number 11. Again, I see this radical. It tells me to write it in exponential form. So I take that xy. Now, isn't that whole xy inside that radical? Yes. Then I'm going to put in parentheses, and I'm going to raise it to a rational exponent. Now remember, the root. What is the root here? It's understood to be a 2. That's the denominator. And since there's no other exponent inside that radical, your numerator is a 1. You got to have something there. So it's xy in parentheses raised to the 1/2. Okay, look at number 12. Again, the entire 8w is in the radicand. It has to be a fractional exponent because it's a radical. The root is my denominator. And since there's no exponent inside, it's understood to be a 1. Okay? All right, moving on. Look at this one. We've got the cube root of 11 squared. Now, you're welcome to take 11 squared and write it as 121, but there's no need. What we're trying to do is write this as a rational exponent. So the base in here is 11. That's the radicand. That's the base of my exponent. And it's raised to a fractional exponent. The root is the denominator. And that additional exponent inside is the numerator. So this is written as 11 raised to the 2/3. Okay? Now, I know 14 can be simplified, but it doesn't ask you to simplify it. These instructions just say to write it in exponential form. So we're writing it as a fractional exponent. The radicand is k, fractional exponent. The root is the denominator, and the exponent inside is the numerator. So k to the 5/4. Now, I want you guys to notice this one's written a little bit different. It has the whole thing raised to the 7th power. So technically, what you have here is you have 3m, and it's risen to the fractional exponent. This is understood to be a 2, so that's the denominator. And since there's nothing else in here, that's understood to be a 1, but it's all raised to the 7th power. So if I rose that to the 7th power, I would simply multiply 1 by 7, and that would end up getting 3m to the 7/2. So what you got to understand is when that's on the outside, like it is right here, when that out here is on the outside, it's treated the same way that this 5 is treated here, the same way that this 2 is treated here. It goes down as the numerator of your fractional exponent. So 3m is being raised. This is understood to be a 2, the denominator. This is the numerator, because it works the same way. So just know that even if it's on the outside, you're skipping a step just knowing that it does the same thing. Okay, next one, we have the same thing that I talked about just a second ago. Your radicand is negative 2a. It's raised to the fractional exponent. The root is the denominator, and this exponent is the numerator. Negative 2a raised to the 5/4. Now I want you to notice the difference between these problems and the ones before. Notice how this part of the radicand is raised to the 5th power. This part of the radicand is raised to the 3rd power. And this part of the radicand is raised to technically the 1st power. Well, since they're all written to their own power, we've got to take them all and separate them. So we're going to write 10 as a fractional exponent. We're going to write a as a fractional exponent. And we're going to write b as a fractional exponent because they're all different exponents inside the radical. Now, what is the same? All of them are under the square root. So the denominator of all of these exponents has to be 2. Now, what about 10? What's the numerator to the 5th power? So 5/2. A, 3rd power. B, 1st power. So it's 10 to the 5/2, A to the 3/2, B to the 1/2. Okay? Hopefully you see that. And then number 9. Number 9, again, similar thing. 9 is being raised to the 1st power, x to the 7th, y is to the 4th. So when I separate all those out, 9 needs to be raised to its own fractional exponent, x needs to be raised to its own fractional exponent, and y needs to be raised to its own fractional exponent. But all of them have a denominator of whatever that root is. They all have a denominator of 3. Now, 9, 1st power, x, 7th power, and y, 4th power. So there you have it. 9 to the 1/3 times x to the 7th third times y to the 4th third. Okay, so pretty simple. I want you to work tonight on the homework from the sheet that you either have or you're about to get it. It's right here. I want you to do numbers 1 through 10. So your homework tonight is 1, 2, 3, 4, 5, and 6, where you actually take each of these rational exponents and you rewrite them as radicals, and then go back the opposite direction on 7, 8, 9, and 10. Okay? We'll save all of the rest of this worksheet for tomorrow. Okay? So, anyways, again, sorry I'm not here. This video is like 40 minutes, so it's perfect. Hope you have a good rest of the day. We'll see you tomorrow.